Okay. So now we'll tie up some of the questions that we have not yet seen or not yet considered. And that is something which is known as the replacement policy. So this is something which is known as replacement policy. And if you want to be exact, you can ask about block replacement policy. So you can call this as block replacement policy. Now, replacement policy is very simple. In direct map. So in direct map thing, there is one index with one tag. So if there is another tag, another block having the same index but different tag, has to sit right here. There is no other replacement policy. It is very simple. But the problem will arise, or the question of replacement policy will arise. Replacement policy is useful for set associative. So for example, you have got this one index and it is, let's say, four-way set associative. So you have got this tag 1, so I'll call it as T1, and data 1, T2, data 2, T3, data 3, and T4, data 4. Once again, T stands for tag and D stands for data. So all these four tags, T1, T2, T3, T4, they all share the same index. And this is, as you can see, it is four-way set associative. I will just write SA. Okay. Now, suppose a fifth tag has to be brought in, say T5. Then which one of this you should throw away? Because T5, because it is having the same index, can sit here or can take place of this or can take place of this or can take place of this. So then you have to decide which data block you want to throw away. You want to throw away D1, you want to throw away D2, you want to throw away D3, or you want to throw away D4. So the policy wise, there are some standard policies, and then companies have designed their own very unique policies which they don't tell us. But let us look at some simple policies. The first one is known as least recently used. Or LRU. Okay, least recently used. So what they are trying to say here is that you throw away a block which has been used a long time ago. So a block is just lying around. So then you just ask yourself that is it a good policy? Then probably you would think that yes, this is a good policy because if I have not used a block recently, it was used long time ago, then why should I just retain it? And that's the easiest one to throw away because probably I'm not going to use it. So on paper, it sounds like a good idea. But in computer architecture or any kind of architecture, there is nothing which is like totally good. I mean, all policies come with some drawbacks. So that if you show me a policy which you think is really, really good for some cases, then I will show you other cases where it is really, really bad. So let's take an example. So I have a block, say block 1, block 2, block 3, block 4, 5, 6, and 7. So I've got my program which is nicely going through this block number 1, block number 2, block 3, block 4, block 5, block 6, block 7. So you may understand that, I mean, there is not much requirement of what should I say? Requirement of change. That there are not too many branches. It is nicely going straight down. And from 7, I have got a loop which is going back to again block 1. Now, if I use this policy, then suppose my cache can accommodate 5 blocks. Just assume. So what would happen is so you started off with the block number 1, and if it was a cold start, so it was a miss, you put it in the cache, then your processor asked for the first word from the second block, it was not there, it was a cold start miss, so you brought it. So now block 2 is in there. Same thing with block 3, block 4, block 5, till here it's all okay. Now block number 6 wants to come in. Now, based on this least recently used policy, block number 1 is the one which was least recently used. So you bring in block 6 and you remove block number 1. Then block number 7 came, you remove block number 2. Then, again, you had to go back to block number 1. Now, where would you put block number 1? Well, least recently used. So what was least recently used? 3, right? So then say, okay, get rid of 3 and put 1 over there. And, you get my point that, then, you will remove 4 and, put 2 and so on and so forth. So this is a corner case. So I'm not trying to say that least recently used policy is a bad policy. But I'm just showing you one example where least recently used policy can cause a disaster. Otherwise, normally it is all okay. Least recently used is also used in some actual design. And more or less, it comes out to be good. But what I've shown you here is a corner case where things can go horribly wrong, right? So this is known as least recently used policy. Then, we used to have something which is known as least frequently used. So the logic for this is that, if some block is not used very often, then, you want to get rid of it. So let us say, and then, I mean, you would agree with it that, that's fine if block is just lying around and, it has not been used. So here it is not the one which was used last time, but you put a counter with each block that how many times that block is used in near future. And you remove the block which has got the lowest counter because then it is not used that often. So it is good to throw it away. And probably you would agree that, yeah, this is a good policy. I mean, what's wrong with it? But let me show you the dark side of it. So I mean, things can go horribly wrong in a case like this. Suppose you have a program which is using it is 8-block program. Then there is a loop like this, which is going on, say, 1,000 times. And then, at the 1,000th iteration, you come out, you go through 5, 6, 7, 8. And then this one also goes around 1,000 times. Okay. So now here, look at this problem. And, my cache size, just suppose, again, to be fair, is like 5 blocks. So it asks for block number 1 and you put block number 1 in the cache. It was not there. So cold start miss, you put 1. Then again 2, cold start miss. So you bring it and put it over here. 3, again cold start miss. 4, again cold start miss. But now there is no cold start miss because 1 was already there. So it's great. Your cache doesn't have to go to the next lower level. 1 is a hit. So this keeps on going around 1,000 times. Now at the 1,001th time, you come out of the loop and you require block number 5. Block number 5 was not there. So it's a cold start miss. Then you bring it 5 over here. Now you require block number 6. Now, there is no space left over here. And, you want to bring in a new block. So which block is least frequently used? Unfortunately, block number 5, it has been used only once, whereas all these blocks have been used up 1,000 times. So if you put a counter to them, they would all say that, these blocks have been used 1,000 times. So when the 6th block is needed, you will unfortunately have to trash this and put 6 over here. For 7, this again would be trashed and put 7 over here, and so on and so forth. So this is one corner case which I'm saying can cause a problem if you use a replacement policy called LFU, or least frequently used. Okay. So does anyone have any question between these two, least recently used and least frequently used?
Sir, hello, sir.
Okay, so let's move on. So this was the second. The third one
Sir,
is a totally interesting thing. It is called random replacement. So that means take any block and throw it away. And sometimes when the user has not written a very nice structured program, at that time random replacement is as good policy as anything. So say in this particular case, it's a very corner case, but here you may say that random policy would have given you better result than least frequently used. So random policy is also sometimes used that you take any block and throw it away and replace it with something else. So that is known as random replacement policy. So these are the 3 replacement policies. There are many other replacement policies which are proprietary to each processor company. They come up with some complicated replacement policies based on some learning algorithm. But at the moment we are looking at 3 possible ways which are quite simple to give you an idea that there is something called as replacement policy. So once again, to sum it up, you have possibilities. There are 3 possibilities. The first one, if it's a direct map cache, then replacement policy is very simple. That if you want to bring in say tag number which has got the same index number as some other tag number which is lying there, you replace it, right? So there is no other question. There is nothing like frequently used or recently used or anything. If a particular block wants to occupy a certain index and that place is already occupied by some other tag, you throw it away and put this tag in. But the replacement policy comes into picture for set associative memory. For fully set associative memory, it is the big case is the biggest, because in fully set associative memory, technically there is no index. All memory levels can lie on tags can lie there, because tags would be the size of index minus the block bits. So then anything can go anywhere, and in that particular case, replacement policy is absolutely needed. So before we wrap this up, does anyone have any question?
Sir.
Okay.
Sir.
So now, multi-level cache design consideration. So now that we have designed the cache, okay, I lost my camera. So let me get it back. Okay, am I visible to you? I believe I can't hear you. Can someone try to speak again?
Sir.
Okay, let me try this.
Someone can say something, just a test message or something.
Hello, sir.
Yeah, I can hear you. So does anyone have any question to ask me? I believe now I can hear you.
Sir, in the replacement part, can we use the policy that if any block is dirty, then we will not replace that block. And since the non-dirty block is already updated, so in worst case, we'll still be able to find in one lower level. So
yeah, sure.
can we
I
do
mean,
that?
that is definitely a good policy, that you try to avoid throwing away dirty blocks, because as you have rightly figured out, that if you want to throw away the dirty block, has to return back to the lower level of memory, so it wastes time. So as much as possible, don't waste or don't try to throw away dirty block, and keep it as long as possible into the particular, wherever it is lying, and throw away non-dirty block. Yeah, so it's that can be incorporated. You can design an algorithm like that. Anything else? Comments, questions? Okay. So now we are looking at how do we design a policy that, how do we design a great replacement policy, and not only replacement policy, but how do we design a great memory hierarchy? So if someone asks you that, what kind of L1 cache would you like to design? So our primary concern for L1 cache is the fast hit time, right? We are ready to sacrifice a miss rate for the ease of access time. So for example, for L1 cache, my biggest worry would be a short time for a hit. That means seek time should be minimum. It should be as fast as the processor speed itself. And if it is slightly lower, then I mean, to do that, I have to design a small cache. Then I have to make it only direct map. So naturally, my miss rate would increase, right? So I'm ready to sacrifice my hit percentage. So I'm ready to make do with something is a hit rate of 90%, 95%, or some such number. But I'm not ready to sacrifice my access time or a time for a hit. That has to be one cycle. And that means the speed of my memory access should be same as that of processor speed. So that means it would say, I want smaller block size. I want smaller cache. Now, you may probably have figured out that why smaller block size is good. Smaller block size is good because to bring a block from next lower level memory to the current memory level requires transfer of a block. And if your block is too big, then the transfer time is too much. So then the L1 cache would say, okay, make the block sizes as small as possible. Make my cache as small as possible. Now L2 cache has got opposite view. And L1 cache can afford to be small, that means compact and small block size and allow slightly higher miss rate because it knows that there is L2 cache, which is quite close in terms of timing. So maybe say 10 cycles. I'm giving this round numbers, 1 cycle, 10 cycle, 100 cycles, so as to, not to confuse ourselves, with lots of calculation. I mean, the real numbers might be different, but it is just to give you an idea. So after 10 cycles, going to L2 cache entails a penalty of only 10 cycles. No, 10 cycles by itself is not a small penalty, but still, it is much less than 100 cycles, which is involved in going to main memory. So L1 cache can afford to have higher miss rate, but L2 cache cannot afford to have higher miss rate because from going from L2 to main memory, there is a large amount of cycles required, let's say 100. So your L2 cache has got different priorities. L2 cache may say, okay, time to access, I cannot do it in one cycle. So, time to access the data can be large. So 10 cycles. But my miss rate should be minimum because there is a term for AMAT, which says miss rate into miss penalty. Miss penalty is anyway very high, 100 cycles. So my miss rate should be as small as possible to reduce AMAT. So L2 cache has got different design priority. It would say, make my block size larger so that, I don't have to go to the next main memory and bring another block. So, this block should have sufficient data to go one by one. Then the second thing is that, the size of the cache should be large. So larger cache can have more blocks. So probably the whole program might sit in there and, you don't have to go to main memory for any conflict misses. So L2 cache design has different priorities. So for L2 cache, hit time is less important than miss rate. So probably now you would have understood this. Does anyone have any question in the design part of L1 cache and L2 cache? Okay. So this again is the same thing, which I put it in a different way. So this is the final thing about cache sizing. So this is a three-way matrix. This is the cache size, this is associativity, and this is block size. So then, there is like, I mean, this is the thing which you have to design, that, there is, say, factor A and factor B. And, it goes from good to bad and less to more. Then, you draw a curve like this and, something with the middle. This point might be your sweet spot. So you have to choose your sweet spot based on cache size, block size, associativity, then, write through versus write back, what policy you want to use. So there are engineers who work on memory hierarchy design all their life and, come up with the best cache sizes and best replacement policies and best write through versus write back, what they want to do. So these are some of the things, a good cache designer does all his or her life. So a processor architect, if you go into, say, performance or processor architecture design, you would be writing a simulation, in C++ of a processor or a memory system, and you keep on doing experiment, by changing some parameters, again, checking it. And they are the people who give inputs to the main or chief architect of a processor that, I mean, this is what you want, this kind of memory hierarchy you should design. Having said that, I also want to remind you that memory hierarchy is a good idea only because of the two properties of your program. One is temporal locality, and second is spatial locality. If you have written your program in a very bad way, suppose if you have written a program which is going in random direction, like, going from memory address X to memory address X plus 1000, then coming back to X plus 200, and, going all over the memory, then, your memory hierarchy is going to fail. In fact, you would be better off not to have memory hierarchy. You will be wasting more time. So memory hierarchy is a good idea if you are able to write nice structured program. And, that structured program can take advantage of memory hierarchy and can give you a good result. And finally, I also talked to you about what we call as real-time processors. In real-time processor, you have something known as tightly coupled memory. So that means no hierarchy, just one level of memory. So accessing any memory location will take same amount of time. So you will not be troubled with cache misses, and, if cache miss takes place, then, you have to have certain amount of penalty. So then, the complete execution of program is sort of a gamble that, it can be finished very quickly, or it may take a reasonable amount of time. And it all depends on cache hit or cache miss, or, how many times it has to go all the way to main memory. So if you want guarantee, or you want to have surety that, my program would execute within this much amount of time, then, you have something which is known as TCM, or tightly coupled memory. So that is just one level of memory. There is no hierarchy. And then, it is easy to determine how much time the execution of the program would take, which is the requirement of a real-time system. So we stop at this point, and our memory hierarchy thing is over. In this particular, especially at the second year level, you have acquired a really good amount of knowledge of cache memory hierarchy. If you understand these things well, then, you can catch up on other principles, which can come in, say, actual industrial design of a cache or memory hierarchy. Does anyone have any question? Okay, so we move to some other topic. I wanted to finish one topic Just give me a second. Okay, can you see this? So this is something which is known as how to write a good structured program which would avoid cache misses. So here's a program is written that, you know, a compiler has to choose between improving instruction level parallelism and improving cache performance. Now, instruction level parallelism is good if you are using multi-core system and you want to divide up your program into, say, 4 parts or 8 threads, so that, you know, each 2 threads would work on 1 core. Most of you guys have a quad core laptop and 2 threads can run on it. So if you can divide up your program into 8 parallel threads which are independent, then they can work in parallel and give you the answer in a short time. So this might be a good time to tell you the difference between CPU and GPU. Now, you know, you must have heard of, say, Intel CPU is quad core, or, you know, ARM CPUs or Cortex A77 is octa core. Or, I mean, actually, it is not octa core. That means it does not have 8 cores. It has got 2 quad cores put together. But, you know, let us not get into the small details. So in 8 core machines, and, you know, maximum you will hear about is 8 core. If you talk about i9, Intel i9, you know, you may hear about 10 core machines or some such thing. But, you know, that's about it. On the other hand, if you look at your graphics processor, it has got like 1,000 cores, right? You know, 1,000. Even your 2 GB RAM, 2 GB graphics processor which you are using, or some kind of NVIDIA graphics card which you are using, it got 1,000 cores. And, you know, if you go on to the higher level, you know, you get 100,000 cores, and, you know, a lot of other issues are there. And if you are a serious gamer, and, you know, you can get this graphics thing which you can get as a separate entity with its own cooling fan and everything. And, you know, you can connect it to your laptop using a Thunderbolt cable. And, you know, and of course, Thunderbolt cable has got very good data rate. So, you know, it can support the graphics on your laptop. That graphics card thing alone uses up 200 watts of energy. I mean, so of course, you cannot put it on your laptop. You know, if you put that thing on your lap would burn up. So it's a separate thing. So then the question is, how come general purpose processors have octa-core or quad-core, whereas graphics processor has got 1,000 cores or 10,000 cores? The idea is simple. First of all, your speed of a core. So, I mean, I would like to tell you the difference between processor and a core. So this is just a difference between processor and core. So if you have, say, quad core thing, so this processor would have 4 identical copies. So core 1, core 2, core 3, core 4, right? Now, don't take this as a law of physics. Now, there is nobody can prevent you in calling this as processor 1, processor 2, processor 3, processor 4. So your Intel, when people say Intel i7 quad core processor, that means in that processing system, you have got 4 identical copies of the same processor. So then, you may say that, how would this 4 cores be useful to me? So one possibility is that, you divide up your work between cores. So you say my word processing or my PowerPoint, which I'm doing, will work on core number 1. My say downloading and video and browsing would be done on core number 2. Core number 3 might be doing downloading, and core number 4 might be doing my camera work or input and output of images. So that is known as coarse grain parallelism. That you are dividing up the task between various cores. But then there is another kind of parallelism which says, okay, they have got one task which is very complicated. So, for example, graphics. Now I want to share my graphics thing. Can I divide up that particular task itself into various parallel threads? So in graphics, it's very easy. So I can explain it to you either mathematically or I can explain it to you in a layman's term. So first let me explain it to you in a layman's term. See, when you see video frames or a picture frame, a pixel over here has nothing to do with a pixel over here or a pixel over here or anywhere in the frame. So the idea is each pixel has its own calculation. It does not depend on the results of other pixels. So this means that, graphics things is eminently parallelizable, and you can have as many cores as you like. In fact, theoretically, you can have as many cores as there are pixels. That, each core would work on a small number of pixels and, would generate things. So that means that graphics or parallelization of task is very, very much possible in graphics thing. So for that kind of thing, 4 cores is great. I can divide up my work into 4 cores. So now then, what people said was that, for graphics, I want a totally separate thing. I want something which is known as graphics processor. I want, say, 1,000 processors. Right? So 1,000 processors inside. Because, my task is eminently parallelizable. So I can divide up my task into 2,000 threads, and each thing would get 2 threads, and, they would calculate it. So that's what your graphics processor is doing. My general purpose processor, on the other hand, is I have maximum of 4 cores, and it specializes in doing serial tasks. So let us get this thing straight. Everything in life is not parallelizable. So some programs, it is inherently serial. So especially recursive programs, so whenever there is recursion, so this result depends on the previous result, that is a serial program. You cannot parallelize it, because till you don't get this result, you can't start calculating this. So you can also say there is a dependence. So if you don't finish this, you can't start this. So you can't start 2 things in parallel. So then, you require a processor or a processor core which is very fast. So here each core in the modern processor of Intel is running 2.5 gigahertz. Now you may say that, why it is not running at 5 gigahertz, why it is not running at 10 gigahertz? The reason is simple. Frequency is directly proportional to power. So higher the frequency of a processor, more power it uses. And more power it uses, the side effect of a power is heat. You'll see that, your processor gets heated up to 100 degrees centigrade. So, actually, if you touch the processor small IC, not the casing, but, touch it inside, you'll burn your fingers. It gets that hot. So if you try to jack it up, your chip would burn up like that, right? So if you have got a processor which requires to service single task, which is not parallelizable, which is serial, and if you want to do it fast, then you have to have a processor which is very fast, means more frequency. On the other hand, graphics processor is a very special purpose processor. It works only for graphics. And in graphics, you can divide up your work into 1,000 parts, or you can even divide up to 10,000 parts. You depend on as many cores as you have. But each of this core is running only at 200 megahertz, right? So that's a big difference between graphics processor and your general purpose processor. So individual core is running at slower speed. But since there are 1,000 of them and the task is divided up into 1,000 cores, your graphics processor can come up with a complex figure or complex video very quickly. So that is the reason why individual core of a graphics processor is slow as compared to your general purpose processor core. But there are a whole lot of them in graphics processor, because the graphics processor is working on a specialized task of things which requires matrix multiplication. And if you study the books on mathematics, maybe later on you would study that matrix multiplication problem is known as eminently parallelizable. So it is also called embarrassingly parallel program. So even you can get as much parallelism as you like. So that's why it works very well on graphics processor. On general purpose processor, you get a mixed lot. Sometimes some programs are recursion based. So you can't do or solve next instruction till the previous instruction has given result. So, it moves in like single file. So to do that program quickly, your processor has to be very fast. Otherwise, your program will slow down. So that is the difference between your general purpose processor and your graphics processor. So now, you should be able to answer that why my graphics processor has got 1,000 cores, but my general purpose processor, which is pulling the load of, everything, has only quad core or at most octa core. Does anyone have any question between graphics processor and general purpose processor? Okay, so now moving on. When you write a program, you will have sort of a dilemma that, should you write a program which is parallelizable or it is cache friendly? Then, you may say, I would like to have both. But, there are some cases where that is not possible. And here I have given one case. I will send the slide set to you. It is part of the problem which I asked earlier, a practice problem. So at the end of that, I have put this small example to show you that, there is how can you write a cache friendly program? And every time you may not want to write something which is cache friendly, but you may want to, and then that's the reason why you should study computer architecture. You decide that you want to write a program which is parallelizable between several cores, or which will be running on a single core, and then the cache misses becomes important. So this is this program. It's a very simple program. You can look at it. You can even write yourself in a C program. So this is a small code. Now this code accesses the data in order they are stored, thus minimizing the cache misses. So I mean, this is really good. I mean, this is what we studied earlier. The data in order they are stored, but their data is accessed the way it is stored. But look at this. If you unroll the loop, so what does the processor do? It unrolls the loop so that it does not have to go through the decision condition many times. So if your loop has got set 100 kind of iteration, if you can open up the loop 4 times, that means you remove the condition of checking and just do the same operation 4 times, and then at the end of 4 operation you check, and then again you do 4 operation. That is known as unrolling of the loop. More you unroll the loop, less number of conditional statement checking you have to do, because conditional statement checking is not a useful work. It is all you are doing is checking the termination condition, or whether it is terminated or not. So suppose your compiler knows that this program has to iterate for 100 times. So let me open it up for the first 4 times, and I don't have to do checking in between. And I can put 4 copies of the same loop in one line. Of course, I mean, it is not as simple as that. You may have to change some of the things in the program, but on the whole, you will be able to open up the, say, 4-line loop. So instead of just, and which has to be done 100 times, you open it up, remove the condition checking statements, and then rest of the instruction you put one after the other. And then, so you don't have to check for conditions. So branching is gone. And because the branching is gone, you can just, any program, which is serial, you don't have branch, can be executed very fast. So if you open it up like this, there is something you will see that, this first element is this, second element is dependent on the calculation of this, and then third element is dependent on the calculation of this, because this is used as an input. The output of this is used as input of this. So you can immediately see that this is not a parallelizable program. You cannot do this, 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 and this independently. These 4 instructions cannot be executed independently. Why? Because there is a raw hazard. So this is a very cache-friendly program, but it's not a parallelizable program, right? On the other hand, if you want to do parallelism, the loops can be interchanged. So when you do this, you will get something like this. And I want you to do it on your own. You will see that this and this has no correlation, and they are all independent. The only problem here is that the cache accesses would slightly become problematic. So this is a good thing, or this way of writing program is great if you are parallelizing your program on 4 cores. And of course, each core has got its own cache. So this problem, you are not using a single cache. At least first level cache is independent to each processor. I mean, we'll talk more about it when we talk about multi-core. Then this way of writing a program is better, though it is not cache friendly, but it is parallelization friendly. So now you have to make a choice depending on the task that you are doing, depending on the processor on which your program is going to be implemented. You can make this choice whether to make it parallelization friendly or cache friendly. Any question on this? Okay. I wanted to start a new topic, but the time is too less. I don't think I will be able to reach up to or finish that thing, and I wanted finish that thing in one shot. So this is what we are going to do for the rest of the semester. We have just finished an important topic on memory. In the coming few lectures that we have, I want to finish two topics. One is superscalar processor, where you have multiple instructions. So your execution unit, there are several execution units, and those execution units can work in parallel. So number of instructions can go in parallel. So so there might be say 2 or 3 say ALUs. Then 3 multiplication instruction can go in parallel. And then execution may be faster. And the idea of a superscalar processor is that if you want to reduce your CPI from 1 to below 1, right? So in inline processor, the best CPI you can think of is 1 cycle per instruction. But what if someone says, I want 2 instructions per cycle? I want that kind of machine. So the idea is have a superscalar machine with parallel execution thing, and probably you can do things faster. And it has got its own problem. It has got then war and wow hazards will be introduced, which were not there in a inline processor. And after we finish that, we'll go to just get a glimpse of multi-core processor, so that we can, or when you finish this course, you have got a complete idea. And probably now would be a good time to check your knowledge. So when you buy a new phone or a new processor, please read about the processor carefully. How much information the company is going to give you, and what does it mean. So someone says that your graphics card has 4 GB of RAM, or it has got 2 GB of RAM, then you understand what the graphics card is for and what it can do. Then then there are always questions that should I get i7 processor with 4 GB of RAM or i5 processor with 8 GB of RAM? Which one would be better for me? Well, then the question is what task you are going to do. Programs can be divided up into 2 parts. One is compute intensive. So that means it requires a lot of computation and the data is not that much. So, one of the examples, probably you do not know about this, but the calculation of the value of pi using Monte Carlo method. So in that particular method, the output of that problem is given as input to the problem. And basically you are trying to calculate the value of pi to a very high decimal numbers, after say 100 digits after the decimal points, or 1000 digits after the decimal point. So in that particular case, it is known as a compute intensive task. So you don't require too much data coming in. Once the data is coming, you don't want anything coming from the memory. Only the execution part will depend totally on the power of processor to finish the task. So those are known as compute intensive tasks. So in that particular case, you require as fast a processor as you can get with as high a frequency as you can have. And you don't really care for, how much memory you have or, memory structure. On the other hand, there is a data intensive. So sort of a problem like, you're getting something from the website, it is more or less a data intensive problem. There is a lot of IO and, a lot of things coming to the memory. From memory, you're putting into your processor. Matrix multiplication is somewhere in between. The calculation is simple. It is called MAC operations. That is multiply and accumulate, right? Matrix multiplication is nothing but series of MAC operations. And in that particular thing, you do get a lot of data, but the operation which you perform on the data is the same. So there's single instruction, multiple data, or people call it SIMD. So in that particular case, it is more or less a data intensive task. So there you require a lot of memory and and fast connectivity between the processor, because the limitation of the calculation will not be the speed of the processor, but your memory architecture, that how fast your data can be brought into the processor and how fast it can be taken out of the processor. So this is all about data intensive and compute intensive tasks. I'm showing you the small nuggets, which are very important for a talk with someone, who is coming for interview and, may ask you these questions. So I'm putting this particular things and so that, you know what they're talking about. Does anyone have any question in this up to this point? Anything from memory before we wrap it up? Okay, so apparently not. So I think this is the last lecture before a small Diwali vacation. We will not meet on Monday after the Diwali vacation. So the date would be, let me say, our Diwali vacation. So we will not meet on 8th. Okay. So class of the 8th is cancelled, and I will make it up in some other way. The question that, can you put the slides on? Yes, I will put the slides. And I wish you guys a very happy Diwali and a very safe Diwali. Enjoy your vacation, and we'll meet after Diwali. So to everyone, very happy Diwali, and to Gujarati students, happy New Year also. Thank you.
Happy Diwali to you, sir. Also.
Thank you. Thank you very much.
Happy Diwali, sir.
Thank you.
Happy Diwali, sir.
Diwali, sir.
Happy Diwali, sir.
Okay.
Diwali, sir.
Thank you very much.